Hi there. In this video, we are going to spend some time solving the classical wave equation. Some of you may have done this exercise in a previous math course, and so this would be a bit of a review for you, and others may have never seen this before at all. So I'm just going to walk through this in a bit of detail just to set up kind of the process that we are going to be using when we start diving into the Schrödinger equation. So the classical wave equation is the equation that governs the motion on a string, and it's used to develop the Schrödinger equation in quantum mechanics, which is why we care about it. So the approach to solving the Schrödinger equation that we're going to use very shortly will be very similar to solving the classical wave equation. So the work that we do in this video will look very familiar to you when we start tackling our Schrödinger equation. Okay, so let's set up our wave on a string system. So what we're going to do is picture a uniform flexible string that's stretched between 2 points. So this will be very similar to the situation we saw when we looked at the vibrating string demo in the physics lab. It would also be similar to a guitar string. Okay, so the displacement is represented by the function u of x of t, right? So we have position and time variables coming into play here. So this kind of displacement would be similar to plucking a guitar string. So one thing that we're going to keep in mind as we go forward is that we're going to restrict ourselves to relatively small displacements or vibrations, and that's just because that gives us the best approximation to this wave equation model. Okay, so the equation of motion of the string is derived from Newton's second law and results in a lovely partial differential equation. We're not going to go through all the details of where this equation comes from, but if you're interested in those details, you can go check out the Appendix A in Macquarie, and that will walk through that for you. So this lovely boxed equation right here is our classical wave equation. U represents the displacement of the string, so this is where we're plucking our string, creating a disturbance. And then v is essentially a velocity, the speed at which that disturbance is going to move along our string. Okay, so here we have our partial differential equation, our classical wave equation. So just looking at this more closely, we see that we have two independent variables, x and t. So that means that varying one of those is not going to change the other. The u is dependent on x and t. We call that a dependent variable. So if x or t change, then that's going to change our value for u, for that displacement. Okay, so the equation is a linear partial differential equation, and that is because our u of x of t and its derivatives appear only to the first power, and there are no cross terms that pop up in there. All right, now for the fun stuff. So now that we've set up our classical wave equation, we want to solve it and get some solutions. Okay, so the solution is obtained using a very common method that you might have encountered, again, if you have done a differential equations course called separation of variables. Okay, so we're going to walk through the details of this approach to solving the wave equation for those of you who are, again, not familiar with this method. So for our separation of variables, the first step that we want to do is to assume that our function u of x of t factors into a function of x only times a function of t only. So that is now represented by this equation here, where we have a big X of x and a big T of t. Okay, so then we're going to just substitute that new expression back into our classical wave equation up here. And when we do that, we end up with this following equation here. Okay, so now we have big T of t and big X of x. I was not very consistent with that, so I will try to add in these little factors. If I forget those, you can just assume that they're in there. Sorry, that's just a lazy shorthand notation that I fall into occasionally. Okay. So now we have started our separation of variables. So the next step here is going to be to take this equation that we have ended up with. You'll notice here that my d's have changed. So I've gone from partial derivatives up here in the classical wave equation to ordinary derivatives down here. So that's one of the nice things about doing this little substitution, is that it allows us to move into ordinary differential equations rather than the differentials. It makes life just a touch easier. Okay, so here is our equation that we're working with now. We have our ordinary differential equation. So now we want to separate our variables. So we want to have one side contain only x terms and the other side contain only t terms. So the trick to getting that situation to happen is we are just going to divide by our expression u of x of t equals x of x, t of t. Okay, so if you do that, you will have the following result. And dt squared. Okay, so you can go through, you can pause the video right now and just kind of verify for yourself that that exercise works out. Okay, so now we have a nice equation here where we have all of our x's on the left-hand side, all of our t's on the right-hand side. So we have now separated our variables. Okay, so far so good. Okay, so one thing we want to remember is that x and t are independent variables. So remember, we can change x while keeping t constant. This means that our left-hand side of our equation, okay, our x, must be constant even if x is varied, because the right-hand side can be kept constant. Right? So remember, we can keep t constant while changing x. Okay, so what that allows us to do is to set both of these parts of our equation equal to a constant. Okay, and we are just going to call that constant k. So you can just say equals k. And we'll figure out what the value of k is later, but for now we're just going to call that our constant. Okay, so now we have our separated variables. We've set each side of that equation equal to a constant k. So now we just want to rewrite them. Okay, so we'll take our left-hand side first. Okay, so that's our d squared x of x. Oh, and I keep forgetting my little symbols. Okay. All right, so we have d squared x of x over d x squared minus k x of x equals 0. Okay, so again, pause the video, go through, do that rearrangement on your own so you can see where that came from. But all we're doing is just taking this left-hand side, our x's, right, and just setting everything equal to 0, so getting that k on the other side. Okay, and then we're going to do the same thing with our t part of our equation. Okay, so just rearrange that, get everything on the left-hand side, and you will end up with the following expression. Okay, so once again we have now our ordinary differential equations. We have one equation in terms of x and one equation in terms of t. Now, one additional thing we want to note with these two equations is these have a very specific form of equation. These are known as what we call homogeneous linear differential equations with constant coefficients. Now, that's a mouthful, and I will abbreviate that as an HLDECC. Okay, homogeneous linear differential equation with constant coefficients. Okay, so HLDECC. Okay, why am I fixating on this name of these equations so much? Well, it turns out that there's a nice solution to this type of equation. So your job in life right now is to be able to recognize this form of an equation, okay, where you have your second derivative and then just a constant here times your variable. Okay, so whenever you can recognize this form, right, then you're going to be able to use the general solution that we have for this HLDECC. Okay, so for those of you who aren't familiar, this differential equation, or these two differential equations, are homogeneous because everything to the right of the equal sign is 0. So we've kind of manufactured that part of our equation there. Okay, so let's just start with the differential equation in terms of x. Okay, so Macquarie, if you take a look in the chapter that covers the this wave equation exercise, okay, Macquarie shows that our constant k, okay, here, he shows that k must be a negative number for everything to work out nicely in our world. Okay, so here we can say that our k is equal to negative beta squared. Okay, so all that's saying is that we will know that k is negative if our beta is real. Okay. All right, so there are other options, obviously, for our constant k. But again, take a look at Macquarie and it'll go through the other options and show that they all give trivial solutions that are not helpful for us. Okay, so we're going to stick with the option for k being negative. Okay, and we're going to plug that beta into our equation above. So then we have d squared x of x over dx squared plus beta squared x of x equals 0. Okay, so the reason that this is nice is that knowing that we have an HLD-ECC form of an equation here, we know what the general solution to that equation is. Okay, so life is nice for us here. So the general solution to our HLD-ECC is this form of equation. And if you are familiar with waves, if you've ever plotted waves in maybe a physics course or a math course, okay, this form of equation is going to look very familiar to you. Okay, but really the important takeaway for us here is that this expression, this boxed expression here, is the general solution to our HLD-ECC in terms of x. Okay, so now starting with our general solution to the HLD-ECC, okay, our next step is to apply the boundary conditions for our particular system. So remember our picture that we started with of our string between 2 points. So we know something about our boundaries. So we know that at x of 0, okay, so at one end of our string, so I'll just draw our little picture up here again. Okay, so we have 0, and we'll call this other boundary L. Okay, so at x of 0, right, our equation, our boundary is 0, okay, which tells us that our A is 0. Okay, now is a good time to maybe pause the video and double check that result for yourself. So just plug in 0 for your x's. Okay, you have to remind yourself of the values for cosine of 0 and sine of 0. Okay, but take a minute and verify that result for yourself. Okay, and then we're going to do the same thing with our other boundary. We know that our other boundary over here at L, right, 0 as well. Okay, so x of L also equals 0, but since we have already A equal to 0, we know that that means our B sine beta L has to equal 0. Okay, so now let's think about this a little bit. There are two ways to satisfy that, to satisfy our second boundary condition. Okay, the first is, well, we can just say that our B equals 0, okay, but since A is already 0, that's just going to lead us to what we call a trivial solution or an unhelpful solution for us. So this does not get us anywhere interesting. So remember, A is already equal to 0. Okay, it's not, that basically leaves us with nothing to work with. Okay, another option would be for this sine beta L part of our expression to be the part that equals 0. Okay, so we could have sine beta L equal to 0. And in order to satisfy that situation, we know that that beta L term has to be equal to some integer number times pi. Okay, so n equals 1, 2, 3, and so on. Okay, again, if that is not jumping out at you, just go review your sine functions, okay, and you can plot those and see that your sine of integer numbers of pi should come out to 0. Okay, so now we're in a good spot here. So you'll notice that the other thing you should note is that our n's start at 1. We are leaving out the n equals 0 option. Okay, that would also lead us to what we like to call a trivial solution. Okay, so we need to end up with something when all is said and done, so 0 does not do that for us. Okay, so only options for n are going to be the integers 1, 2, 3, and so on. Okay, so then that leaves us with our final result when we put everything together. X of x equals b sine of n pi x over L. Okay, so, all right, that is one of our solutions. Okay, so remember we are just plugging in, so you're going to solve for beta here. So here beta equals n pi over L, and we'll plug that back up here because we want our general form in terms of x. Okay, so now don't forget we also have to do the same thing for the time part of our wave equation. So we just did x. Now we're going to go through and do the exact same thing for t of t. So remember here was our homogeneous linear differential equation with constant coefficients for the time portion of our wave equation. We already know what the general solution is to that sort of expression. Again, remember the beauty of recognizing an HLDECC, right? We already know what the general solution to that is. So we end up with a general solution for the time part of our wave equation given here, where we have a little bit of a different notation since we're dealing with the time domain than we had for our x domain. So we just have this omega popping in there. We have an omega t inside of our sine and cosine arguments. So omega n can be represented by our beta constant times the velocity here, or since we've already figured out what beta is earlier when we did x, we can also say that omega can be represented by n pi v over L. Okay, so our next step, if we are comparing to what we did for the x part of our wave equation, we would apply boundary conditions to try to get some values for those d and e coefficients out here, but time domain, we don't have any boundary conditions, so we can't get the values for our d and e, so we're just going to leave them there as is. Okay, so then if we put everything together, put the x and the t, results from our separation of variables solutions, put everything together, we can have a lovely equation for our full u of x of t for a given n, for a given state, which is this wonderful equation right here. So we have our result from the time, solving the time part of our separation of variables method, and then we have our result from x. Okay, so here we have f and g. Remember, those are new coefficients. So remember before we had d and e and a and b from when we solved our equations individually. Okay, so all F and G are doing here are just combining our constant coefficients from the two equations we're putting together. So the A and the B and the D and the E, okay, they're just combining into new coefficients here, so don't worry too much about that. So our n's, again, still, n can take on values of integers, 1, 2, 3, so on and so forth. Okay, so the real take-home message here is now we have a full solution to our original differential equation. Each one of these u of x of t's is going to be a solution to that wave equation. Okay, and each one will represent one particular mode of vibration of our string. All right, but one thing that we want to keep in mind is, remember, when a string vibrates, it's usually not just going to vibrate according to one single value of n. Okay, so we're going to have multiple modes essentially that will be activated when we pluck our string. So it's important to look at what happens when that's the case. So if we put all of those different vibrations together, it turns out that the sum of all of those vibrations is also a solution. So just a little bit of a different notation here. This looks really similar to what we just had before, but just pay attention here. We now have a capital U, okay, big U, and no n in there. So this is going to represent our overall general solution. Okay, so this is it turns out to be what we call a Fourier series. Okay, if you're not familiar with that term, feel free to go investigate that a little bit further on your own. But this is a standard type of equation that you'll encounter in physics and math. But here we just have a Fourier series that satisfies our classical wave equation, and this equation can represent any motion of our string. So not just one mode, but really any kind of motion that might be possible. And so we call this our general solution to the wave equation. And just a few final points about what we've done here. This procedure that we've used to obtain the general solution is possible because, according to the principle of superposition, now this is something that's going to pop up throughout the semester. We're going to see this idea of superposition of states a couple of times down the road. Okay, the important take home for that idea is that for a homogeneous linear differential equation, which is what we've been dealing with, if x1 and x2 are individually solutions, then the sum of x1 and x2 also ends up being a solution. Okay, so we're going to use that idea of superposition of states and the idea that if we have two solutions to a problem, then the sum of those solutions is also going to be a solution. Okay, so hang on to that idea. That's going to pop up again down the road for us. And then just one other little note that the coefficients F and G, those just represent different strengths of the different harmonics that are coming into play. And so this is why our different instruments sound different. So that's kind of cool. Okay, and last but not least, just the cherry on top for our discussion of this wave equation solution is, why does this matter for chemistry? Why did we bother to just go through all of this mess to get this general solution for vibrational modes of a string? Well, if we look at our general solution that we just ended up with, okay, it turns out that we can get a nice physical interpretation from this equation if we rewrite it a little bit. So it turns out that this term right here, this cosine plus sine term right here, can be rewritten in this form with the cosine omega t plus phi. Okay, so there's actually a homework problem in Macquarie that has you verify that this expression is equivalent to this expression. So all we're doing here is rewriting it in a little bit of a different form. And what I'm going to point out with that is that our first term here, okay, we can think of as the temporal part of our vibration, and this the sign n pi x over L would represent our spatial part of our vibration. So for most of our discussions, we're going to focus on the spatial part. We're going to put that guy into use a lot in the near future. But this whole general solution, okay, is a nice description of that motion of our wave, right? Its time development and its spatial development. Okay, so we like to think of each of these individual u of x of t's, the little u's, those individual modes, we call those normal modes. So normal mode is a term that you'll hear pop up a lot when you're talking about vibrational spectroscopy. So that's a term to commit to memory. You're going to hear that again. So a normal mode is simply just a standing wave that oscillates with a certain frequency. Okay, so taking a look at this new form of our general solution, okay, remember that u of x of t, right, that we've now come up with is essentially the same as saying it's the sum of all of our individual modes that are solutions to our equation. Okay, so remember each one of these is a normal mode. Okay, so this is similar to the vibrational modes in molecules. So like CO2, you have your CO2, your symmetric, asymmetric vibrations, your bends. Okay, so each one of those molecular motions is essentially one normal mode. Okay, so each normal mode in our wave equation here represents a harmonic motion of frequency, where our frequency, this is a nu. Okay, so let's be clear. Remember, the difference between our nus and our v's is very important. Okay, so this would be a frequency. Okay, that's our nu. And then that is related to our angular momentum. Sorry, not angular momentum, angular velocity, omega over 2 pi, or also n times the velocity of our wave over 2L. Well, remember, L is the length of our string, or the bounds of our string, I should say. Okay, so remember this one is not a frequency, but a velocity. Okay, so that's a V. All right, so I think that should cover all the important bases for us. So hopefully that was either a good review if you've already done the solution to the wave equation in a previous class, or hopefully you can go back and revisit any parts of the video that you need to make sure that you can follow exactly how we did that solution using the separation of variables method. All right. Like I said, we will be using these techniques as we start tackling some of our first quantum chemistry systems, okay, some of our initial models. So you're going to see a lot of these ideas come back into play. All right. Hope that was helpful. Thanks.